Welcome to Brain Vision.
So here we're going to let the kinetic energy of the system be the kinetic energy of the two masses, since the rod is treated as massless. So A would be the heavy mass or heavier mass, and we can say that B would be the lighter mass. Therefore, the kinetic energy would be equal to 1/2 the moment of inertia of the heavier mass times the angular velocity of the heavier mass squared, plus 1/2 times the moment of inertia of the lighter mass times the linear velocity of the lighter mass squared. We can say K would then be equal to 1/2 times ma r sub a squared omega sub a squared plus 1/2 m sub b radius sub b squared omega sub a. Because the angular velocity, we can say b and then specify that radius of a equals radius of b and omega sub a equals omega sub b. So then the total kinetic energy would be equal to 1/2 r squared omega squared times the sum of the masses. And we can solve. So K would then be equal to 1/2 times 0.210 meters quantity squared multiplied by 5.60 radians per second quantity squared multiplied by 7.00 kilograms. And this is giving us 4.84 joules for the kinetic energy. This would be your answer for part A. Now for part B, we want to find the net force. So we can say, for part B, we can say that force sub A would be equal to m sub A r sub A omega sub A squared, and simply solve. So 4.00 kilograms multiplied by 0.210 meters multiplied by 5.60 radians per second quantity squared. This is equaling 26.3 newtons. So that'd be the force associated with the mass A. The force associated with mass B would be m sub B radius sub B omega sub B squared. However, again, the radius and the angular velocity are the exact same. The only thing that changes is the mass. 0 kilograms, but then 0.210 meters, and then again 5.60 radians per second quantity squared. This is giving us 19.8 newtons. Now, we know that these forces are exerted by the rod because they are unequal. We know that there would be a net horizontal force on the rod due to the masses, and we know that the horizontal force would then have to be counteracted by the mounting for the rod in order for the rod not to move horizontally. There's also a gravity force on each mass balanced by the vertical force from the rod. So there is no net vertical force on either mass. So these would be the answers. However, just to mention again, there would need to be some horizontal force that would be counteracting so that the rod does not move horizontally. And of course, there is the gravitational force for each mass. So again, there is no net vertical force on each mass. Because this would be balanced by the vertical force from the rod. Or in essence, it would be the force normal. And then for part C, we can say that we can take the 4 kilogram mass to be the origin of coordinates. And so we can say that the x coordinate for the center of mass would be equal to mass sub A, x sub A plus mass sub B, x sub B divided by the sum of the masses. So this would be equal to 4.00 kilograms. Again, we are taking x sub a to be 0 meters, and then it would be 3.00 kilograms. This is 0.420 meters away from mass sub a, divided by 4 plus 3, or 7.00 kilograms. Therefore, the x-coordinate for the center of mass would be equal to 0.180 meters. However, this would be from mass A. So because the distance from mass A to the new axis of rotation is now 0.180 meters, the distance from the mass B to the axis of rotation would simply be, we can say x centimeter, x of the center of mass would be equal to 0.240 meters from mass sub B, again, given that m sub B is 0.420 meters from mass sub A. At this point, we can then redo the calculations for the total, for basically part A and part B, and say that K, the total kinetic energy, would be equal to, again, 1/2 omega squared. However, now the radius in this case would be different. So it would be m sub A r sub A squared plus m sub B r sub B squared. So now we cannot actually factor out the r. And now we're going to recalculate 1/2 times 5.60 radians per second squared. This would be multiplied by 4.00 kilograms, multiplied by 0.180 meters squared, plus 3.00 kilograms, multiplied by 0.240 meters quantity squared. And we find that the total rotational kinetic energy would be 4.74 joules. So it hasn't changed by too much, only by about 1/10 of 1 joule. However, we do have to recalculate. And then for the forces, now this would be m sub A, r sub A, omega sub A squared, m sub B, r sub B, omega sub B squared. Let's solve. 4.00 kilograms multiplied by 0.180 meters multiplied by 5.60 radians per second quantity squared. This is equaling 22.6 newtons. For mass B, 3.00 kilograms multiplied by 0.24 meters multiplied by 5.60 radians per second quantity squared. This is equaling, again, 22.6 newtons. Note that these are going to be the exact same, and that is because we took r to be the distance from the center of mass. So because the horizontal forces are now equal, there will be no horizontal force on the rod or the axle. Again, they are equal because we chose r to be the distance from that mass to the center of mass. That is the end of the solution. Thank you for watching.